Hello, everyone. My name is Mina, and I'm a PhD student working with Professor Grayscow at the Navigation and Autonomous Vehicles Lab at Stanford University. And today I'll be talking about our work on designing long memory codes for GPS using the cross-entropy method. So we're now about to embark in a new era of GPS navigation. Next year, the navigation technology satellite NTS-3 will be launched to test new technologies and signals for the next generation of GPS. And this experimental satellite platform is actually reinvigorated from its previous initiatives in the 70s during the initial design phase of GPS. And then starting in 2026, the GPS 3F satellites will have the first fully reprogrammable signal, which allows for opportunities to re-explore the signal design, including the design of the GPS codes. And if we take a look at the current codes used in today's GPS signals, we see this includes gold codes for the L1CA signal, which were developed in the 1960s and can be generated with 2 linear shift feedback registers. We also have truncated sets of maximal length sequences, which were developed in the 50s and proposed for the L2C and L5 signals in the early 2000s. And these codes are truncated in order to satisfy a specific desired code length, such as the 10,230 bit length signal for the L5 signal. And these can also be generated from a single shift register. And finally, we have the wheel codes, which were developed for L1C and can be generated from the Legendre sequence. And for L1C, the wheel codes are extended with the 7-bit pad to satisfy the desired code length of 10,230 chips. So we notice here that the current codes are all algorithmically generable sequences, meaning that they can be generated from fewer bits using an algorithmic procedure. And having algorithmically generable codes was an important consideration when GPS was originally designed, and even a few decades after, when receiver memory was expensive and when there was less computing power to search for better codes. However, today, computing power has increased significantly since the early 2000s, with the number of transistors per microchip increasing by about 3 orders of magnitude. Additionally, memory today is an inexpensive resource, both in terms of size and cost, and receivers are capable of storing complete families of GPS codes or memory codes. And in fact, the European system, Galileo, which began launches over 30 years after GPS, uses memory codes in their signals today. And there are several advantages to using memory codes. First, memory codes allow for the flexibility to choose any desired code length, whereas algorithmically generable sequences are only limited to specific code lengths, and they've been modified to satisfy the desired lengths for several of today's GPS signals. Additionally, as shown in this histogram, even a single bit truncation or extension of these codes disrupts their original and coveted correlation properties. Memory codes are also not constrained to being algorithmically generable, which leads to a greater space of possible codes to choose from. And in fact, this space is exponentially large, given that each binary code family has at least about 1,000 bits and at least 50 codes in total. And while this gives us a greater opportunity to potentially find better performing codes, it also presents a key challenge in that we can't use exact optimization strategies for such a large-scale combinatorial design problem. And we can also tailor the design of the memory codes to a particular desired family size, whereas algorithmically generable codes are defined for a specific family size. So for example, the length 1023 gold codes has a total family size of 1025 codes in total, whereas only 63 of these are used and defined in the GPS L1CA interface specification. And this is important since existing lower bounds on the correlation performance of spreading codes depends on the family size. And these lower bounds only increase or get worse with a greater family size. Additionally, we've empirically observed improved correlation performance for smaller code family sizes. So here we have the mean squared correlation performance for the complete gold codes for length 1023 bits in comparison with optimized codes from our prior work for different code family sizes. And we see improved correlation performance or lower squared correlation side lobes when we tailor the design to smaller families of codes. And finally, when designing memory codes, we have the flexibility to optimize for any desired performance objective. So while gold codes in particular are well known for their maximum correlation side lobe properties, prior works have also proposed alternative objectives for navigation spreading codes in order to reflect overall acquisition and tracking performance. And this includes squared correlation levels that exceed the Welsh bound, as well as more generally any p-norm of the correlation side lobes. And prior works have examined memory code design for the Galileo E1, E6 signals for length 4096 and length 5115 chips, and for 50 data and pilot code pairs. And then these prior works have proposed using genetic algorithms, which mimics the process of biological evolution by picking higher performing codes and then recombining these codes at each iteration. And in our prior work, for lengths of up to 1023 codes, we've explored using block coordinate descent strategies or block coordinate descent using convex relaxation strategies to optimize small subsets of bits at a time within the code family. And we've also explored meta-heuristics, including the natural evolution strategy, which represents a continuous probability distribution over the discretized code space, and then samples from this distribution and optimizes the distribution to improve the spreading code performance. And in this work, we explore the use of the cross-entropy method for navigation code design. So similar to our prior work's natural evolution strategy, this method also represents a proposal distribution. However, at each iteration, instead of doing a gradient step update, it evaluates a maximum likelihood estimate in order to update that code distribution at each iteration. And this can lead to larger updates at each iteration and fewer iterations necessary to improve the code performance. We also formulate this approach to have a simple and efficient update step, as we'll discuss more in upcoming slides, which we can easily scale to optimize long families of memory codes with lengths of over 10,000 chips. So in this work, we explore a new code design framework based on the cross-entropy method, which efficiently designs low correlation spreading codes. And we examine code lengths of up to 10,223 chips and family sizes of up to 50 codes. We demonstrate the ability of this method to design lower squared auto and cross correlations than well-chosen golden wheel codes. And we show that the cross-entropy method achieves equivalent or better correlation performance as our prior code design strategies and an analogous genetic algorithm, while converging in fewer iterations. And to the best of our knowledge, this is the first work to design families of long navigation memory codes for lengths of over 8,000 and over 10,000 chips. So with that, I'll first provide an overview on the cross-entropy method before going into the details of how we formulate this approach for navigation spreading code design. So this includes the proposal probability distribution representation and the code design objective and the maximum likelihood-based code update step. And finally, I'll present the experimental results before summarizing this work. So for the greater memory code design space, we use this overall three-part stochastic optimization framework with the cross-entropy method. And we'll first start with the code generator, which models a proposal distribution or a probability distribution over the design space. From this, we sample code families. And actually, the actual memory code design space is discrete and very highly dimensional. But here we illustrate it for in a 2D space for ease of visualization. So here we have the smooth manifold, which represents the objective function we want to minimize. And each sample from this code distribution represents a complete code family within the space of memory codes. And next, we evaluate each of these samples according to our code design objective. And then from these evaluated samples, we find the best performing sets of codes, or the ones which minimize our objective. And these are called the elite samples. And then with respect to the best performing codes, we find the maximum likelihood estimate in order to update the proposal distribution. And then we can repeat this process and we should see our proposal distribution shift toward lower objective regions of the memory code design space. So now going into our code generator, we model the proposal distribution over the memory codes as an independent multivariate Bernoulli distribution. So we have one parameter per bit in the code family. And this represents the probability that bit is sampled as a 1. And then we can sample from this to get each code in our code family of size k codes or k satellite transmitters in total. And for our code evaluation metric, we want both low autocorrelation side lobes and low cross-correlation side lobes. And we choose to minimize the p-th norm of these correlation side lobe levels, where p represents the power that we take these correlation side lobes to, and where a larger p effectively weighs spurious high correlation values more heavily in the code objective. And then we can choose to frame the objective as the maximum of these two criteria to ensure that we minimize both the autocorrelation and cross-correlation side lobes simultaneously without compromising one for the other. And finally, we perform the cross-entropy method update of our proposal distribution, which evaluates the maximum likelihood of the set of elite points. And from how we defined our proposal distribution, we can efficiently evaluate this maximum likelihood estimate, since it simplifies to just evaluating the vectorized mean across the elite set, which is very efficient computation at each iteration. And prior works that use the cross-entropy method have incorporated smoothing of this maximum likelihood estimate update. And this helps improve convergence performance of the algorithm. Okay, and so now I'll go into our experimental results. We compare the performance of the cross-entropy method, which has the details listed in the top table, with that of our prior work in an analogous genetic algorithm. And we compare against the longest code families generated from this prior work, in particular, the length 1023 and length 1031 chip codes. We also examine how the histograms of the auto and cross-correlation values are shaped when we perform optimization for different norm P objectives with the cross-entropy method. And finally, we generate families of longer memory codes, optimizing for the maximum squared auto and cross-correlation objective and comparing against well-chosen families of equal length gold and wheel codes. In particular, gold codes only exist for lengths of 2 to the power n-1, where n is indivisible by 4. While wheel codes exist for any prime number code length. So we generate these same lengths in cross-entropy method, and we list in this bottom table the corresponding code lengths up to length 10,230, which we show results for which we show results for in the paper. But for sake of time, we'll only show results for the length 8191 and 10,223 code families. And then given that there exist thousands of gold and wheel codes for these code lengths, we sample subsets of the total number of codes and save the best performing gold and wheel code family from 10,000 randomly sampled subsets to compare with the cross-entropy method. So diving into our results, here we have the squared correlation performance for the analogous genetic algorithm in blue and the natural evolution strategy in orange from our prior work. And we compare this with the performance of the cross-entropy method in green. And we see the performance of length 1023 and length 1031 codes as a function of the code family size. Now, all of the methods have the same population size and ran until convergence. And the natural evolution strategy in particular was given 10,000 iterations to run. And we notice here that the larger code sets, for those larger code sets, the cross-entropy method achieves similar or better correlation performance than the natural evolution strategy, while actually converging in much fewer iterations for each run in less than 1/10 the number of iterations as NES. We additionally show how the auto and cross-correlation histogram of the spreading code family is shaped by the norm P objective. So we vary the P value from 2 to 4 and 8. And we also compare against randomly generated binary codes in red. And we see that for the norm 2 objective, we have much higher occurrences of lower correlation values that are close to 0. Whereas when we increase P to 4 and 8, we have reduced occurrences of these very low correlation levels and a shift towards medium level correlation values. And at the same time, if we look at the maximum correlation level, we see that for the larger p-valued objectives, we have a reduction in that maximum correlation value as well. And finally, we show the performance for longer memory codes with the squared correlation objective for length 8191 and 10,223 chips. And the autocorrelation performance is shown in dotted lines, whereas the cross-correlation performance is shown in dashed lines. And the maximum between the two, or the value of the overall objective, is indicated by the individual points. And we observe that the cross-entropy method achieves both lower squared autocorrelation and cross-correlation performance than the best golden wheel code families for all sets of these long memory code families. So to conclude, in this work, we formulated a new flexible spreading code design framework using the cross-entropy method, which efficiently designs low correlation spreading codes. And we demonstrated this for code lengths of up to 10,223 chips and family sizes of up to 50 codes. And with this approach, we design codes with lower squared auto and cross correlations than well-chosen golden wheel codes, and achieve equivalent or better performance as in our prior work, while converging in significantly fewer iterations. And finally, to the best of our knowledge, this is the first work to design families of long navigation memory codes for lengths of 8191 and 10,223 chips. I'd also like to thank our sponsors, the Air Force Research Lab and the National Science Foundation, for sponsoring this research. And thank you so much. Please let me know if you have any questions on this presentation or on our paper. Thank you.